Hi, this is Paul again. I've got a new video to show you, and this video I'm calling No Chaos 8. In my last video, No Chaos 7, I focused on the B-type DNA. Now I showed that you could get 5 swirls in an 120-degree section. But when I was converting these zigzags into B-type DNA rungs, I found that the orange zigzag wasn't exactly the right shape. Now look when I add a blue vector zigzag. Now you can see that the blue zigzag is a different shape, the good shape. But to use this vector, all the other vectors have to be reorientated to make a helix. Now I think we've got some important geometry here. So I'm going to add some more geometry here for you to see all this orientation better. And I show some little red balls. They could be icosetas, but that shows how the diagonals are split up with the geometry. I've made a little anim to show it rotating around the axis for you to see this geometry a little bit better. Now you can see the purple, cyan and blue zigzags, and the red balls on the green vector make it easier to see how they are in the correct position. Now we also have a cyan zigzag on the purple vector. Now this is zigzag number 4. Now this is a set of 4 zigzags that are on this 120-degree level, because the green zigzag on an orange vector is on the next floor, and it'll be the number 1 zigzag of a set of 4 that will go from 120 degrees to 240 degrees. Now the white rectangles that I show are the size 6.5 rectangles, and the measurements are in my earlier videos. Now all the zigzags are similar to the purple zigzag, which you can see clear. So the zigzag lengths will all be the same. You can't see this obviously because they all lie at different angles around the vector axes. Okay, I think I'd better bring in the vector system to show you the vectors, because this is a very important piece of geometry. Now look at all the vectors in that center icosa. That's a size 6 icosa. And now you can see that the zigzag length is equal to the center to the icosa vertex. And you know something? We don't really need that third rectangle, because that rectangle could belong to the second arc. I'm gonna chop it off. I think it might simplify things. I guess I'm not the one for big words and complex equations. I think the colored vector system is a little bit more simpler than chaos, but the two-dimensional theorist cannot be told anything. Okay, so we don't need that center vector system anymore, so let's get rid of it. So I think we can say that we've got 4 zigzag rungs on an 120-degree section of B-type DNA. So I think it might be looking very promising. Okay, so we can clean this up to the bare essentials, and what we are really down to is a prime 120-degree helix section that contains 4 rungs of B-type DNA. Okay, let's see this in the top view. And we'll make 2 copies of these sections and move up double root 3 and rotate 120 degrees. And I think I'll show this anim in the top view also. This top view looks a lot better, but we can't see it moving up on the floors. Okay, so now we have 3 4-rung sections of DNA. The vector colors are only correct on the first section. And notice I'm just showing the bare essentials. And notice the center vectors of the helix are matching the colors of the diagonals of the size 6.5 rectangle in the center. I'll hide everything except them vectors and you can see what I'm talking about. This could be a very important feature. Okay, now we'll bring the zigzags back again. So now we have the colors correct for the first portion. So I'll show you the colors correct for the next portion, which is on the next floor. And now I'm going to hide this second portion and bring in the third portion. So now you can see the color coding for the third portion with the vectors. I've shown everything separate to make things look simpler. Now look when I show the three sections together in the top view. Now it's amazing that the 3 phi rectangles are now showing an icosahedron. And the mathematicians that say that only a crank shows trivial geometry is a load of baloney. Okay, now I'll show this going through pretty fast in the front view. And then we'll put all three together. And now we can give it a little spin around. And you can see that we have 3 4-rung sections. We are showing 12 zigzags in total. Each of the 12 zigzags are totally independent to each other with color and orientation. Isn't that something? So this is going to give us 12 independent rungs for B-type DNA. I showed the 3 strings of helix separate, but now I'm going to join them up with a thinner helix so you can see the differences. Now I've been thinking about these prime sections, 120 degree sections. That is why I call them prime sections. I think they will always stay intact even if you start taking bends, because this can be shown with the thin section of helix. Okay, let's take it into the top view again, because now I'm going to bring in a 4 zigzag phi rectangle assembly. Now these phi rectangles are the basics for the geometry for each zigzag rung. Now if you look at the first phi rectangle assembly, you can see that the purple and green vectors are the diagonals of them phi rectangles. Okay, so now we'll bring in the second set of 4. And then we'll bring in the third set of 4 that makes up 360 degrees. Now all of these phi rectangle assemblies can serve as a 2-dimensional foundation for the 3D geometry. So now we can bring in the colored assembly of size 3 and size 1 icosas. So we're looking at a full assembly of 3D geometry for a 360 degree cycle of B-type DNA. I guess this is what they call junk DNA, but now they seem to have changed their mind. Maybe my geometry had something to do with it. Okay, so now we can whittle down to the bare essentials of the DNA. Now we're looking at a set of 4 rungs. And we have another set of 4 rungs, 120 degrees to that one. And we have a third set of 4 rungs, 120 degrees to the second one. We can hide the rectangles, and now you can see plainly that we have a string of 12 rungs in a 360 degree spiral. Now I'll show the first string of 4 in the front view, and you can see as it's spinning around, you can really see what's happening. Now each of these rungs show a pair of colored pyramids. Now I've decided to call these rungs PYRPAIRs. We are looking at PYRPAIR 1, 2, 3 and 4. So now we can go to PYRPAIR 5, 6, 7 and 8. Now if you look in the center, you can see I show a red and yellow vertical vector. Now you can see on number 6 PYRPAIR is red and yellow. Now these colors match up to number 2 PYRPAIR. Okay, so now we can bring in PYRPAIR 9, 10, 11 and 12. And now as it's moving around, you can see that we have a third red and yellow PYRPAIR. Now these 3 red and yellow PYRPAIRs, 2, 5 and 10, all match up to the red and yellow vertical vector in the center. The red and yellow pyramids contain different vectors. Now we show the three sets going around together. And you can see the red and yellow PYRPAIRs have cyan, blue and red icosa vectors. So you can see that the DNA rungs have a perfect three-dimensional mathematical sequence. But I guess the mathematicians only want to spend their time trying to figure out the chaos theory. Now I'd like to just focus on the first four. Let's bring it more to the center. Let's just take a look at PYRPAIR 2, the red and yellow. We have two size 3 rectangles and the size 2 rectangle. I give all these measurements in my earlier video, No Chaos 5. We can't see the size 1 rectangles. Let's hide the icositas. So that's better. Now we can see all the 5 rectangles. Now notice I showed the zigzag, 2 cyan diagonals and a green diagonal. So you can see that everything comes out of these 5 rectangles. So now we'll bring everything back and we'll give it a little bit of a spin around. Now notice that the 5 rectangles are positioned on the center edge of the red and yellow pyramids. They are aligned perfectly. I don't think there's nothing trivial about this piece of geometry. Now let's take a look at this geometry with the full size 3 icosas. Now you can see that the colors are all arranged in the same order between the icositas and the size 3 icosas. I've kept showing this through my videos, that the colors are matching the vectors. This is how three-dimensional order is kept. But the academic professors only focus on chaos. So I guess what I have to say is like talking to a wall. Anyways, let's take the color fill out of those icosas. And we'll give it a little bit of spin around. And it's now a little bit easier to figure out how them pyramids come out of the icosa. Now if you look at my earlier videos, I show that everything starts with the icosita and it builds up to size 2, 3, 4, 5, 6. I show that all the little pyramids kept building up in the perfect order. But I guess this wonderful three-dimensional order in 3D reality means nothing to a two-dimensional theorist. Okay, let's hide everything except a couple of pyramids. And I'm going to show a couple of hexagon-pentagon molecule shapes. I'll just show the outlines on the red and yellow pyramids. Now look at the top hexagon and pentagon. I'm going to rotate it 120 degrees 3 times. Now you can see that the top hexagon can be orientated in 3 different positions to the bottom hexagon. Now let's rotate the bottom hexagon 120 degrees. And now the top hexagon can go around 120 degrees 3 times again. So now we'll rotate the bottom one another 120 degrees. And we have another 320 degree positions on the top hexagon again. So you can see that it's possible to have 9 different pairs of hexagons. Now this will come in handy for the people in molecules to do research. I know very little about this subject. I only realize that the DNA strings they show will come out of this sacred geometry. And I think we have a beautiful three-dimensional order. I think the proof is in the pudding. So this is Paul saying, thank you very much for looking at my video.